Hello guys, welcome to Exam List. In this lecture series, we'll talk about a little bit of more on wave function and I'll introduce you to what do you mean by stationary states in quantum mechanics. Agreed? Okay. So let me remind you what we have done till now. So the reason I have to remind you again and again because quantum mechanics is not that easy like classical mechanics. Okay, so you have to remember everything that I have told you. So a quick revision. So a wave function can be one dimensional, then it is a function of both x and t. Why it is a function of x and t? Because you see this wave function satisfies 1D Schrodinger equation, and 1D Schrodinger equation has time part on the left hand side and the space part on the right hand side. So mathematically psi must be a function of both space and time. Similarly, you have this one, which is a wave function in 3 dimensions, so it depends on all the 3 coordinates x, y, z. This part satisfies the 3-dimensional Schrodinger equation or 3D Schrodinger equation, where the space contains the Laplacian, it contains all x, y, and z, and there is a time part. Agreed? So interestingly, you see that a wave function is a function of both space and time, and you know that square of the wave function gives you what? It gives you probability, that is probability of finding the particle. For example, do you remember particle in a box? So we have already discussed in our last class, so I mean in the last lectures, that if you confine an electron inside a box, okay, and say the potential inside of infinite potential, so the potential at this part is say infinity, and the potential here is also infinity, so the electron cannot go to the other side. So this is what the arrangement is telling you, and the electron is confined in a potential box which has a length L. Then I already told you that if the electron is confined in a box, then the probability for the n equals to 1 state, so these things already we have discussed in our last lectures. So for n equals to 1 state, the probability is like this. um, Let me draw it better. So the probability is like this. So this is quite weird, because this diagram says that if you try measuring the presence of electron, then you'll find that for maximum amount of time the electron is somehow at the center, and this electron spends minimum amount of time at the near the edges of the box. So this is quite weird. Okay, so this is because quantum mechanics, it's a weird thing. So somehow, as I have already told you, if you have two wall, and if you make a ball go hit the wall, come back, so if the ball continuously bounces back and forth, then the probability of finding the ball in any given position is same. That's logical. But quantum mechanically, the probability of electron is more at the center, less on the side. That's illogical, but that's what quantum mechanics says on the first place. Okay, that's why it is different from the classical mechanics. So what am I trying to say? So this particular system has a wave function of the electron psi, which is a function of both x and t. Agreed? You can agree on this part, because we are dealing with one dimension box, because this one dimensional box has the x coordinate only, along which we are calculating the probability. You see the probability is this probability, this red color line that you see, this red color line is what? So this red color line is actually probability as a function of x. So this probability as a function of x has such that it is maximum at the center, and as you go away from the center or from the middle of the box, the probability decreases. Now, so can you tell me one thing? If I measure the, so consider the electron is confined in this box, in this potential box, and I make the measurement, and I find this is the probability, that is the probability of finding the electron is maximum at the center, and it decreases as you go to the sides. If I do the same measurement after 3 to 4 days, do you think there will be any change in the probability or the result? See, what is the result? The result is your measurement. And what is the result of your measurement? The result of your measurement is probability. That is, what is the probability of finding the electron at different places? So amazing thing is that the probability for this case does not change with time. So if the probability is not a function of time, then the wave function for such a system can be written as, you can just break the wave function into space part and the time part. Okay, so this can be written as, say this is some function of time. Now you'd say that psi of x. Okay, so to make it different, what I'll do is, okay, it's okay. So now you would say that, okay, so you are telling me that if in a particular system the probability is independent of time, then the wave function can be separated into the space part and time part. Now who told you that? This will be your question. Well, I can answer that. Remember standing waves? Okay, let us go to our classical wave dynamics that we have studied. So if you have a rope and if you generate standing waves in the rope, what happens? So if it, for n equals to 1, this is the standing wave. Remember, this is how the rope looks when it is a standing wave. Now an interesting thing, so when there is a standing wave, the rope has either in the upward position or in the downward position. Now you might have studied the equation for standing wave. Do you remember? So let me remind you. So for the normal wave that you have studied in your +2, so if I make you remember the wave function for standing wave, you remember that the wave function for standing wave looks somewhat like this. So y is equals to 2a cos kx, 2a cos kx, and there will be the time part, that will be, say, cos omega t or sin omega t, whatever you want you can write. Okay, so let me write sin omega t, cos kx and sin omega t. Agreed? So what do you observe from here? You observe a very interesting thing. You observe that for a standing wave or for a stationary wave, the time part and the space part of the wave equation are separated. Usually wave equation is written as what? Y is equals to a sin kx minus omega t or a cos kx minus omega t. But for a standing wave, if you have read the standing wave, then for a standing wave, the space part and the time part has got separate. This is what you have already done in your basic wave mechanics. Now the same thing applies to quantum mechanics, but you know the problems. You cannot imagine the amplitude. All you can do is you can calculate the probability, which is not the case in the classical wave equation, because you can both imagine what is the amplitude and what is the probability. You can measure the amplitude and you can measure the intensity. But in quantum mechanics, your amplitude is a complex function, so you cannot even imagine the what is wave function, but all you can do is calculate the probability. Agreed? So if you confine an electron in a one dimension box, so this is example that you see on the left is the example of a one dimension box, then what you see is the probability is only a function of space. It is independent of time. Whether you measure the probability of finding the electron at various places inside the box today, tomorrow, 10 days later, 1 year later, things are going to be same. I know you will say that, hey, can you give me some more concrete example? Yes, I can give you some more concrete example. The best example is, consider the Schrodinger equation in 3 dimension. So when you consider the Schrodinger equation in 3 dimension, it means you are working with an electron in 3D. Okay, this Schrodinger equation will little bit get modified, because if you have a consider there is a nucleus at the center and there is an electron. Okay, so this is the nucleus and up we have an small electron. Then there is a particular potential that is generated by the nucleus, which I can write V is a function of R. R means I'm considering three-dimensional potential. So Schrodinger equation will get a little bit of modification. So in case of hydrogen atom, we just add the potential. So I'm not concerned with that. But all I want to say is that the another stationary state, by stationary state I mean the state in which the probability of finding the electron does not change. So another example of stationary state is atom. Electrons inside an atom, that those electrons are stationary states. That is, if the particle is in a state of definite energy, such as an electron in an atom, in an orbit, or definite energy level, the value of probability at each point is independent of time. Such a state of microscopic particle is called stationary state. What do I mean to say is that, see, here the electron is in a particular energy level. That's why I say this is in a stationary state. Hence, the probability. What is this blue diagram? This blue diagram is the probability of finding electron. Agreed. So this is, I guess, the S state, S sphere, and this is my say P. Okay. Now look at an interesting thing about S. The probability of finding electron on the S is same everywhere, and but there is an interesting thing about P. So the probability of finding an electron in the P state is either at the top. See, so electron is either found at the top or the electron is found at the bottom, but the electron is never found anywhere near the nucleus. So how do you draw the P state? You draw the P state as like this, remember. So what is the meaning of this state? Say consider this is a 2p state. So what is the meaning of this 2p state? This 2p state is saying that there is a nucleus here. I'm not drawing the nucleus. So there is a nucleus here, and this is how the electrons are distributed. So consider this state has 2 electrons, 1, 2. Then these 2 electrons are either found on the top of this. So these 2 electrons are either found here, or the electrons are found here, but the electron is never found at the center. Then you will say, if the electron is never found at the center, then how the electron is crossing, how the electron is going from upper lobe to the lower lobe without even crossing the center? Well, that's a miracle. This is how electron behave. It never crosses the center, but somehow it goes from one lobe to the another. This is a truth. This is a big truth, whether you believe it or not. So this is the probability distribution of electron in the S. This is the probability of distribution of electron in the P, as we have already discussed. So this is the higher cells, and these are the probability distribution. Now you say that, okay, I understand probability distribution that you found out by solving the Schrodinger equation in 3D with Coulombic potential. But what about stationary state? You said something about stationary state. Yes. Why I'm discussing these diagrams is because these diagrams will never change. Agreed. These diagrams are not going to change with time because these are stationary state. Have you ever heard that the electron in a stable atom, the electron, if it is found in the 2s cell, it is already found in the 2s cell until and unless you give some external perturbation. I mean, consider you have an atom. If you don't give any heat or light to the atom, there is no transition of electron. Everybody is happy and everybody is in their own position, and the probability of finding the electron in their position is constant with time. They never change. The same as the 1D box, where I said that the probability of finding the electron for the 1D box does not change with time. Similarly in 3D, by 3D what do I mean? I mean the electrons inside an atom. So they are very happy. They are in their own position and their probability does not change with time. So probability of finding the electron in 3D depends only on the space x, y and z, and this probability never changes with time. However, if you take an atom and you give some light or you give some heat to the atom, yes, the probability will change because there will be transition of electrons. So we are not going to that part. So all I'm saying is you have a simple atom, no perturbation from outside, the probability distribution of electrons will be constant with time, they will not change. These states are called as the stationary states. So what is the specialty about stationary state? The specialty about stationary state is that the probability is independent of time. Since the probability is independent of time, the wave function can be broken down into the space part and the time part separately. Wait, we are not finished. Let me rub this all so that I can explain you why probability is independent of time. This will be your another question. So the question is, if I break the wave function, which is a function of space and time, now if I break it into the wave function which depends only on space and a function that tells me time, then I claim that the probability, so what is my claim? That probability is independent of time. And you know what probability is? The probability is square of the amplitude or the square of the wave function. Now question is, how the hell this happens? Let me tell you how this happens. You see, these functions are actually of form e to the power minus I, okay, minus I e by h cross t. Okay, this is actually the function, and this is my psi of x, and this will be my complete wave function. So a complete wave function is both function of space and time, and if the wave function is a stationary state, then it can be broken down into space part and time part. Now what is actually psi of x and t whole square? Okay, this has to be understood. You see, as I already mentioned, that psi is a complex function. So psi square is what? Psi square is probability, but psi is a complex function. And remember that the square of a complex function is always psi star, that is psi star psi, that is conjugate of psi into psi. So that in turn can be written as psi, which is a function of x and t, and take its conjugate and then multiply with the normal psi, which is a function of x and t. Now what is the meaning of conjugate? Conjugate means the I will become minus I. Okay, you already know these basic things of mathematics. So if I do a quick calculation, what will happen? There will be a psi of x, okay, and there will be an e to the power, I guess there will be a plus, so there will be a plus because conjugate means the minus I will become plus I, so plus e t. Okay, so assume h cross as 1. In many people do this so that we don't have to write h cross again and again. In later lectures I'll tell you why h cross is taken as 1. So just take it, so I don't have to write. And for the second function I'll be having psi of x into e to the power, yes, there will be minus I e t. Agreed? So now you can see that the time part, they cancel each other, and all I am left is I'm left with only the space part, the square of the space part. Hence you can see that the probability, look at the probability for stationary state is independent of time. So I hope you understand what stationary state is. Stationary state means the quantum system whose probability does not change with time. These are called stationary state, and stationary state occurs when the quantum particle is in a state of definite energy. So what is that energy state here? The definite energy state here is E, because you see in my equations I have written E. So if the electron is found in a particular energy state, only then it is a stationary state. Now how is the Schrodinger equation for a stationary state written? Okay, so this thing is a bit tricky, so let us see. This will convince you a lot of things. Okay, so usually how is the Schrodinger equation written? You know, Schrodinger equation written as I h cross. Okay, we have already discussed the Schrodinger equation in our last lectures, what it means, from where it came, so I'm not going to that detailing, but you know that Schrodinger equation is written in this form: I h cross del psi by del t, and this side will have h cross square by 2m. I don't think there will be h cross there. Yeah, I don't think there will be h cross here. So I d psi by dt is equals to h cross square by 2m into d square psi by dt square. Agreed? Now, for stationary state, this part will not happen, because you see this part is saying that the wave function is dependent on time. But as I said that for stationary state, the wave function should not depend on time. So now the question is, what will be the Schrodinger wave equation in case of stationary state? Well, yeah, there will be an h cross I h cross t. So in case of stationary state, we actually write E psi is equals to minus h cross square divided by 2m del square psi divided by del t square. Okay, so if you want me to write a more general Schrodinger equation taking into consideration the potentials, then what I'll do is I'll write v of psi. This v is an operator that acts on psi. So if you want me to write more general Schrodinger equation, I can write a v of psi here. We'll discuss about this v of psi in our next lectures, so why it is written. But we have already discussed from where v of psi has come. But for now, just know that for stationary state, this is the Schrodinger equation. Now you see that this Schrodinger equation has, oh, this is, so this will be my x, agreed? So this will be my x. So you see that this Schrodinger equation is nowhere dependent on time, because there is no time part in this Schrodinger equation, as a result of which the wave equation for this Schrodinger equation will be the solution of this Schrodinger equation will be psi of x only. So what is the solution of this type of Schrodinger equation? The solution of this type of Schrodinger equation will be in terms of only x. There will be no time, because we know anyhow the time will get cancelled when we square it. So this formula is called time dependent Schrodinger wave equation. Okay, it's called as the time dependent Schrodinger wave equation. And the solution, and we, so I hope you understood what you mean by stationary state. Stationary state means the quantum system is in a state of definite energy, as a result of which the probability will not change with time. Now question is, can I give an example where the probability is changing with time? Okay, that will be better. Let me give you an example. So consider you're doing some experiment. Okay, so consider you have a screen. Okay, and on the screen you are doing an experiment where the electron is coming and hitting on the screen. Okay, some quantum experiment. I'm not going into the what is happening in between, I'm not going to that detail. But consider you did the experiment at time t equals to 0. So when you did the experiment at time t equals to 0, you find that maximum electron has reached the center, and many of the electrons have reached the edges. Okay, so when you did the experiment with time t equals to 0, now something happened when you did the experiment after 10 seconds. So when you saw something weird. What you saw? You saw that on the same screen the probability pattern has shifted here. So the maximum electron is here and minimum number of electrons are here. So you see, in 10 seconds there is a shift in the probability of finding the electron. I mean, there is a shift in the position in which the probability of finding the electron was maximum. In 10 seconds, the position in which maximum electrons were being found, it got shifted and it reached a new position, and this new position is now the position where the maximum electron is being found. So in 10 seconds something happened, and you see that there is a shift in probability. This type of experiment where the probability is changing with time, in those cases I can write that my probability is a function of x, yes, and my probability is a function of time, because as the time is going, the probability shape is changing. So understood? So understood the difference between stationary states where the probability is not changing with time, and this particular example is a example where the probability is changing with time. Agreed? So in the next lecture, we'll discuss more on quantum mechanics, wave function, Schrodinger equation, etc. Thank you for listening. Bye bye.